Good morning or good afternoon, all. Today I'll be talking about a way of looking at climate change, a diffraction experiment for the multiple views, the multiple ways that we as engineers, designers, scientists, policymakers can and do engage in looking at climate change. And to do that, I'm going to be building off of the movie The Matrix. So within the movie The Matrix, there is a moment where our hero character, played by Keanu Reeves, faces Morpheus, another hero character, but basically the mentor to Neo, which is Reeves' character. And he offers a blue pill and a red pill. And Reeves is faced with this choice. Does he want to wake up into the challenging world of seeing the Matrix for what it is, and it's really a dystopian future, or take the blue pill and go back into a state of dreamlike virtual reality that allows him to imagine as if things are just being solved by normal day-to-day practices of technology in America. Okay? So if you haven't seen The Matrix, I highly recommend just watch the first one. It's a dystopian future. It goes right up there with Blade Runner and the Mad Max movies as a demonstration of a future that is not, say, utopian in a sci-fi sense, in a speculative fiction sense, but it is dystopian. And the blue pill and the red pill are going to be used for our diffractive thinking. Rather than, remember, we're thinking through reflective thinking versus diffractive thinking, and basically diffraction allows us to look at the problem from the margins, where we will exclude from mattering some core issues and really look at the issues that are happening at the margins and that are happening for marginalized people. So here's the blue pill. And over on the right is the quote from The Matrix. You take the blue pill, the story ends. You wake up in your bed and believe whatever you want to believe. Now, the blue pill is, as echoed over on the left, remaining in blissful ignorance of an illusion. As we see in the cartoon, I'm not worried about global warming. Technology will save us. And we see a drilling rig that is right over here. That is part of technology that is actually causing a lot of challenges for us, right? And we need an energy miracle from Bill Gates. And the thing that we don't see in our technology will save us, we need an energy miracle, the classic viewpoint of the global north, predominantly the Europe, North American West, but also emerging through Asia, through China, that a lot of the prosperity, a lot of the progress, quote-unquote progress that we see came about through a heavily extractive process of people in the African continent and other nations in the global south, in South America. And you're seeing this picture of looking for self-determination, women's rights, land rights, all these things, food justice, are coming through as major problems, major challenges for many nations, but they're really exacerbated in the nations on the African continent. The solutions that are suggested here are to drop tech. And I'm using this very explicitly. To drop tech on people is basically to just, give them a cell phone. Give them a solar panel. If somebody is having troubles, just give them technology. They'll get better, right? the idea of engineering new solutions to get us out of the problem that engineering new solutions got us into, that is the illusion that dropping tech on people will solve their problems. When in fact, what people solve problems. Technology emerges from the people part of the problem. Now, coupled to dropping tech in what we will come to know as 1, 2, 3 engineering is the extraction of resources, and one of those extractions is to appropriate people's ways of doing things or appropriating culturally significant ways of doing things. Appropriating is a form of theft without acknowledgement, right? So we do see scenarios where engineers will take a technological idea that has been an intergenerational type of process and effectively appropriate that, re-engineer it, and then drop that tech back on the same group of people for a cost. So something that was free gets taken, gets turned into a profitable, marketable, bankable technology, is dropped back on the people, and what happens is an exacerbation of the problem that we're talking about. So if our problem is climate change, we're exacerbating it by drilling more oil and using oil money or using oil technology to develop carbon capture, carbon storage technologies, when we know we have other solutions that will take social change. Let's say. So this is giving you a view of the blue pill. It's what we would call it is a techno-optimistic perspective. And why not look at this through a diffractive thinking pattern? So what you're seeing here is on the lower right, a basic tool that I use in solar design courses, that I use when teaching optics and teaching transfer of energy as light, is you've got the curved line that is an emergent or an emissive source of light, in this case shortwave, that's the SW. So the curved line shows that that's a source of light, in this case shortwave light, and that light has a lifetime. And the lifetime goes and transmits through space, through a vacuum, through air, and upon becoming incident upon a surface, a particle, a wall, your skin, it has a combination of phenomena, including reflection, that's the green bounce with the character rho for reflectance. It is absorbed into the material, a sink, so go source to sink, energy transfer, but it's light. And remember, light is all forms of electromagnetic radiation, so that can include Wi-Fi, that can include cellular transmissions, that includes the visual light that you see. Okay? And the sink is to be absorbed. So the little grounding lines that you're seeing there is actually light absorption in our diagrammatic way of doing that. But the thing about reflection is reflection always is in reference. It is representative of something. So the reflected light on the mirrors of Morpheus that you saw in the first slide is a representation of Keanu Reeves' character Neo looking at the two choices of the blue pill and the red pill. Now, diffraction is an optical phenomena, just like emission, reflection, absorption are optical phenomena, but diffraction is a quantum phenomena, and diffraction patterns are basically light bending around the corners of a diffraction grating, is what we call it, a diffraction grating, bending around corners and interfering constructively and destructively, light interacting with itself. So the upper right, where we see this little 532 nanometer emission of light, that's a green laser, and that's why I drew that as green. Green lasers are typically have a central mode of light emission that is about 532 or green nanometers. So diffraction diagrammatically is this little loopy diagram where we see that light is being constructively emphasized in green in diffraction patterns. So you have a central beam in the middle, that's the core beam of light where the most energy goes through, but where in fact we want to be looking at are on the edges where the diffraction patterns are, where the fringes of the diffraction pattern are happening. Oftentimes we will exclude that core beam. Let's just say, I'll put an X on this. We'll exclude that core beam and only focus on the diffraction patterns, which are noticeably less intense than the core beam, but they provide far more information to the structure and to the relations of materials. And in the case of the chemical or physical tools that we use with diffraction patterns with a reciprocal space, like X-ray diffraction patterns, we also find these in Fourier transform, infrared, FTIR, but we look at the fringes to find the chemical and structural information. And the interesting thing here is that when I'm looking at a diffraction pattern of white light of many, many wavelengths, what I find is that on the fringes, I have these rainbows. So diffraction creates rainbows. And in this particular way, like in the diffraction phenomena that you'd see on the back of a Blu-ray disc or a DVD. Diffraction patterns themselves have been the topic of some modern philosophy by Donna Haraway and by Karen Barad. So diffraction patterns record the history of interaction, interference, reinforcement, and difference. That is physically what diffraction patterns are recording on a digital surface, on a wall, etc. But diffraction gets used here as a way of thinking in the same way that we say, hey, I'd like you to reflect upon the way that you decided to take a career in engineering. Instead of, that's a reflective thinking process. Reflection is a scattering of light, a bounce of light that goes backwards and then is perceived by eyes, etc. Diffraction is light intra-acting with itself. So intra-action is a broad term from Meeting the Universe Halfway, the book. And light is intra-acting with itself. Photons are touching each other. They're touching themselves to create superpositions of each other that then creates basically interference. And interference is a physical term, positive, or that talks about constructive and destructive interference, which if you look here, we'll see this dark black space that is destructive interference, light waves, amplitudes and troughs overlapping and canceling each other out, whereas the brighter lines are the constructive interference. Okay. In the case of in-phase coherent light sources like lasers, this is from a classic optics textbook by Hecht, just called Optics. We have a situation in which the amplitudes are added first and then squared to determine the resulting flux density. The flux density is like the irradiance of light. The superposition of coherent waves generally has the effect of altering the spatial distribution of energy, but not the total amount present. So we're getting all of the data that we need in a diffraction pattern, and it gets the spatial distribution of light no longer looks like a photograph. It looks like rings in 2 dimensions, or what we would call a diffraction pattern, ring-like diffraction pattern. But all of the energy of all of those lights is, oh, you're just hearing a beagle bark over there. All the diffraction of all the energy of all that light is still contained within the image. And so we get to the red pill. So the red pill from the movie. You're seeing in the lower side. I think that's in the second or third episode of the movie of The Matrix. Remember, again, the first one's the only one that really, conveys this core philosophical idea of taking the blue pill and the red pill. You take the red pill and you stay in Wonderland. And I show you how deep the rabbit hole goes. So, like, the idea here is that reality is this strange and crazy wonderland, and the connectivity of so many different things in our world today, much like the real world of the Matrix, is where making a difference happens, and it makes a difference that matters, that has a matter-like effect. You physically are changing things. The genesis of this as a red pill is that you're in the Matrix in the movie. The dystopian future is that humans darken the skies or scorch the sky. And here's the quote from the movie. "We don't know who struck first, us or them, but we know that it was us that scorched the sky. At the time, they were dependent on solar power, and it was believed that they would be unable to survive without an energy source as abundant as the sun." Now, this is artificial intelligence. These are machines, robots that have taken over the planet and are now using humans as in little incubator chambers to be a source of energy for their life. And they created the Matrix to make humans a source of energy, to extract energy from humans. The sometimes painful truth of reality there is that we're living in a shitty place right now, in the Matrix. And the idea is like, well, that's a dystopian movie. That's all messed up, right? And that doesn't happen here. Well, in reality, here, now, we have scientists. Hang on one second. We have scientists right now who are talking about replicating what happens in volcanoes. So there are sulfur-rich volcanoes that belch out sulfur dioxide, which has historically been known to darken skies. And the classic example of this is the Mount Tambora explosion of 1815 that caused a year without summer in 1816 in Europe. Across the planet, actually. So hold on. So to launch sulfur dioxide or sulfuric acid effectively into the stratosphere to darken the skies is what is actually being looked at in a global warming scenario. All right, let's see if we can get back into pace. We now have moved Harry the Beagle, who is having a barking contest with his other beagle roommate, Molly. They're now upstairs. Okay, so scientists are actually thinking about darkening the skies. And it will not be as dystopian looking as what you've got down here. But yeah, really, people are actively looking at blocking out sunlight, the thing that, gives us light, because we are just dependent on solar power for plants, for photovoltaics, for so many different things, in an effort to use technology to dampen the effects of global warming driven by solar irradiance. This doesn't change the fact that the oceans are acidifying through carbon dioxide dissolving into the ocean, but here we are. It's a painful truth of reality that technology alone is not going to solve our problem. We have to engage people. We have to engage stakeholders. And we have to be aware that light from the sun is not so easily turned off, that it has systemic effects, that it will actually lead to very strange, nonlinear responses if we are to do, say, geoengineering of light in the stratosphere. Okay? Blue pill, red pill. So you ask yourself, well, what can we do? Well, you can make a difference that matters. And it will include technology. This is not like independent of technology. And inside of the matrix, everybody uses technology. It's just that you're making a difference that matters to the stakeholders in their given locale. All right? Okay. The context that I want to bring in is basically tied to the Little Ice Age. So earlier we had you watch videos from Brian Greene from discussing the Little Ice Age on YouTube. And effectively, the Little Ice Age ran from about 1300 through about 1820. I say 1850s here, but basically the early 1800s, the Mount Tambora explosion that I just described was basically like the last concluding event of the Little Ice Age. And the Little Ice Age was basically a time when the light, the annual irradiance, dropped. So you physically had a drop of about 2 watts per square meter. That doesn't seem like much, right? This is where the small temperature changes on the global scale are really, really significant. But the Little Ice Age was the coldest time in the last 8,000 years. And you see 1290 to 1490 is where you get a first start. The 1500s were marginally okay, but then by the time you get into the 17th century, you get some really nasty times. And this is the times where women were burned at the stake as witches in Europe, where the mid-Atlantic slave trade was exacerbated and turned into chattel slavery. I mean, it was already there, but where things just kept on getting worse and worse across the planet. And socially, there were more wars. There were more people dying of famine. There were droughts in West and Central African nations. Right? It was a bad time. Okay. Before you look at this, like the stability of this, like instability, we know about something called the Milankovitch cycles. Milankovitch cycles are effectively the Earth and the orbit of the Earth, the spinning of the Earth leads to these kind of sequences that happen over the course of thousands of years of the planet, where the solar forcing, mainly like the light going up and down in annual solar irradiance, has been associated with a cooling phenomena over the last 2,000 years. So what we would call the Quaternary Ice Age has been happening for about 2.5 million years. So we're in a cooling phase in terms of a very long time scale. But that is not the origin of instability for the Little Ice Age. The origin was volcanoes. So there was a sequence of what we think from the geologic record, 4 major volcanic eruptions that were concentrated around the Ring of Fire, around the island rings around the Australian continent, around Australia, around New Zealand, right? You see Samalisi in Indonesia erupted in 1257. Vanuatu is a tiny island that is currently being consumed by global warming. It will be an island no more in about 100 years. It's also a spot where Kauai was the caldera now for a major eruption that was also dumping sulfur-rich gases. So this would be sulfuric acid gas. That is, basically there's water vapor in the air, and so if you're a volcano belching out sulfur dioxide gases, it turns into acid rain. that acid rain, if it's high enough in the stratosphere, does not make rain, but actually makes particles of salt, sulfate salts, that are increasing light reflectance. So basically, if you think of like salt as white, it's reflective, right? So you're not seeing darkness because of light being absorbed by a dark material, but this is like how when you're in an airplane and you're flying above clouds, it's always brilliant white, whereas underneath those clouds, it's a dark storm, right? It's dark underneath clouds, fly up above them, and it's brilliant white, and what clouds are doing is reflecting shortwave light. So in this case, the sulfate salts, the aerosols that are high up in the stratosphere, are reflecting sunlight. That rho, it stands for reflectance. There's a net energy balance to light that is 100% of light, or 1, has to be balanced by the light that is incident upon a surface, either being absorbed, alpha, reflected, which is what we're talking about here, or transmitted, which would happen if we just had, say, nitrogen and oxygen in the air. Light is transmitted, shortwave light is transmitted through the sky and gets absorbed by the earth. But if I have clouds, if I have sulfate salts, that light is reflected back out into space, and it affects the energy balance. And so if I look over on the far right, what I've got is a reinforcing feedback loop that says, as I reflect the incoming light, I decrease the amount of light that gets to the Earth's surface, that's G. And I decrease the amount of light that is absorbed by the Earth's surface, that's S. And remember, absorbed light on Earth's surface is what changes the temperature. So if I have less light absorbed, the temperature of the Earth, T sub E, is going to decrease. And as the temperature of the Earth decreases, here's the nonlinear feedback. You get more glaciers at the poles. You get more glaciers in the mountains, the exact opposite of what we have been experiencing in climate change warming. And what that means is more glaciers means more reflected sunlight permanently. And so you get more temperature drop, which leads to more decreased light. And it's a reinforcing feedback loop. This is a systems loop. The R is for reinforcing. What we would call this also in systems thinking would be a positive feedback loop. Negative feedback loops balance, positive feedback loops reinforce. So what? Well, the weather changes. That's what so what. WX, by the way, is a shorthand for weather. It's not a resilient system. When you destabilize the climate, you destabilize the weather patterns, the fingerprints of the seasons and the weather patterns, which then shifts the way that insects behave. It shifts the way that people move. We have wars, we have famine, we have disease. It is really rough. Now, as Brian Greene said, we also do get Shakespeare out of that. So there's that. But overall, we're talking about a pretty rough time ahead of us. And it's already happening now, right? So tie this back to energy and light. Basically, the energy constraint response is a phenomena that we describe. It's a hypothesis that I've developed over many years to describe the why people go for solar versus other times where they just ignore it. And the energy constraint response is this: for periods when fuels such as wood, coal, oil, gas, when fuels are constrained locally in a region, in a culture, societal innovation ultimately leads to solar system solutions, making a change that matters. For periods when fuels are unconstrained, solar is communicated across society, across the arts, as being diffuse, intermittent, weak, insufficient. This should sound familiar in our oil and gas rich society of the United States, and coal, and nuclear power, and. The types of fuel constraints that can come about are going to be fuels being constrained by being physically inaccessible. So if something physically inaccessible is, say, like deforestation of the Italian peninsula, where we started getting solar design in Greece, in the Italian peninsula across China when people were deforesting entire regions. And so there was no longer accessible fuel. And so it leads to, culturally, building design changes. Limited access from policy and law. So in Germany in the 1970s, there were a lot of protests about nuclear power development. And so the German government said, okay, what do you want to do? And that started the Institute for Solar Energy in Freiburg, Germany, which became now the global leader in one of the global leaders in solar energy research for electricity. If fuels are economically inaccessible, so imagine that you're living on an island where the only access to energy as electricity comes through a diesel generator, in which case your fuel, diesel, has to come from off the island, and it really drives up the cost of everything. High risk for access is a type of constraint that says if I needed to get, say, cobalt for batteries, for lithium-ion batteries. Cobalt tends to be in a lot of them. I take a lithium cobalt battery. I need the cobalt. The cobalt comes from or is mined in areas that are war-torn around People's Republic of Congo. There are basically mineral reserves only in certain countries, and it's a high risk to get that. So like all of these things together are types of fuel constraints that can happen and have happened continuously through history. And one of the reasons why we are looking at climate change through the Little Ice Age is because it gives us a historical way to think diffractively think, about the problem, the situation that we have at hand. The core of the Little Ice Age was that climate change happened and all sorts of weird stuff happened. That's the core beam. If we look at the margins and why did it happen and what can we learn, what differences mattered in that we can use in design thinking, in systems thinking, to engage people, to engage change, to make a difference that matters, which for many of us in design, that's why we're here. And so the pushback that comes is that we have technology. We have had technology for a long, long time to solve the problem of climate change. Part of the technology is people and the way that we engage with our environment. So you see this cartoon of two people talking about laundry drying on the line. It says it dries the washing using the very latest technology, a combination of solar and wind power. And yet we have communities that actually have like home ordinances or neighborhood ordinances that say like, no, you can't dry your clothes outside. It looks off-putting for neighborhood aesthetics. When that's one of our routes. Now, I'm not talking about going and living in yurts or something like that. That's a cultural norm that works for people in some regions. Yurts, that is, these tent-based structures. Say if you're living in Mongolia, this is a cultural tradition. We are not looking to appropriate that tradition and then drop it as a technology on us in, say, Pennsylvania, central Pennsylvania, here. It's a different locale. It's a different stakeholder group. But we can use the thinking that emerged from finding solutions that were portable, that were distributed across large regions. We can use the thinking and how people gathered together to find solutions collectively. We can use that through stakeholder engagement within a given locale. And basically why Bill Gates is wrong about climate action, this article up there, is that we have the technology to solve our problems. We don't need, what Bill Gates is talking about is how do we make money off of a new technology for dealing with climate change. We have it. Like solar power has already been around for 50, 60, 70 years. We have it. And what I'm telling you is you have to effectively walk through the door of entangled engineering, where you, the designer, the engineer, are approaching problem solving to systemic problem solving, to solving for pattern rather than solving to make money. I mean, this is all coming together as like we can build careers that do make money. They're just not going to be using the tools of society that has worked for us when we were not as strongly impacted by climate change 200 years ago, right? So the upper left image is from the sequel to Blade Runner. The lower right image is from The Matrix. If I can only show you the door, you're the one that has to walk through it. So we have these images of dystopian futures that incentivize us to get thinking about these things, these futures that can happen. I'm here as a bearer of the blue pill or the red pill to say, look, you can look at this problem and you can either look at it and deal with the uncomfortable truths and then get going to act, to make changes that matter. Or you can take the blue pill, get into a job that makes cool new technology, that does not push you to think about the ethics of why you're doing it. It is done globally as a what we would call a turnkey technology solution, where you just pass it out to everybody. Everybody gets the same solution, no matter where they live, no matter what their principles are. You could do that. And there's no shame in that. I'm here to convey that there is a real strategic advantage to looking at entangled engineering, which we'll be talking about next lecture, through the lens, a diffractive lens, through a grading, where we will look at the margins for stakeholders, for locale. The fact that solar energy, solutions with solar energy are unique to the group of stakeholders in their locale. The goal of solar design is to seek out highest preference for solar goods and services. That would be solar utility. To seek out highest preference of solar goods and services for your group of stakeholders in a given locale. Goal of solar design, using entangled engineering principles as opposed to dropping tech, extracting from people, and appropriation. Okay? We'll pick this up later, but for now, thank you for your listening time and have a good day.